That's right. Okay, so we have been. So this is the sort of the justification for everything I've been telling you now, and of course, I'm not going to do any rigorous mathematics on the blackboard, but I'm just summarizing what is actually known rigorously. So what I've said to you is this. Let me just remind you what we said last time. There is a class of functions called Stieltjes functions, okay? And a Stieltjes function is, remember, is defined as, let's call Stieltjes function f of x. Okay. A Stieltjes function is defined as an integral over a weight function, call it rho of t or w of t, something like that, over 1 plus xt. Okay, that's a definition. Where rho must be positive, okay, for all t greater than or equal to 0. That is all the t in the range of integration. And the integral from, let's give it a name, and a sub n, which is the integral from 0 to n, dt, rho of t, t to the n, so that's called the nth moment of rho, has to exist. Okay, that's a Stieltjes function. Okay, and a Stieltjes function has 4 properties. That's what I was saying to you right at the end of the last lecture. Okay, and these properties are that that f of x is analytic in the cut x plane. Okay, and that means with a cut running down the negative axis. Okay, so except on the negative axis, everywhere here in the complex x plane, this is the x plane, this f of x is a Stieltjes function, is an analytic function. Okay. Okay. Again, analytic means that it has a derivative in the sense of a complex, in the sense of complex variables. Okay. So remember, analytic means f prime of x exists, okay, as a complex derivative. Okay, so complex derivative exists. Okay. Second property is that f of x goes to 0 as x goes to infinity, in the cut plane. So if you go off to infinity in some direction, except on the negative axis where f doesn't exist, where it's on a cut, okay, if you go off to infinity, this integral here has to vanish. Okay? And the third property is that f of x is asymptotic to the series minus 1 to the n, a sub n, x to the n, okay, in the sense of an asymptotic series, as x goes to 0, and the argument of x lies between minus pi and pi, okay? So if you go all the way up to here, you're at an angle of pi, and if you go all the way down to here, you're at an angle of minus pi. And so as you go to 0 in any direction, this series is asymptotic to that function, okay? And this series is called a Stieltjes series. Okay. And the last thing you need to know is, let's raise this up a little bit. Okay. Last thing you need to know is that that f of x is, or let's say minus f of x is Herglotz, which I think, as I said to you last time, it's a great word. I can think of funnier names, but that's pretty good. And it is easy to show, or relatively easy to show, that all four of these properties are true, okay? And let me remind you, Herglotz means the following, to be very precise. Herglotz means that in the upper half plane, that is where the imaginary part of x is positive, okay, in the upper half plane, that is where the imaginary part of x is positive, the imaginary part of f of x, in this case minus f of x, the imaginary part of minus f of x, is also positive, okay? And in the lower half plane, where the imaginary part of x is negative, the imaginary part of minus f of x is negative, okay? And these are the four properties, very important properties of Stieltjes functions. So that's pretty restrictive. I mean, obviously, not all functions have that property. Let me see. So we need to say a few things. How do you prove things like this? Well, proving number one is easy. How do you establish that number one is true? So how do you establish number one? Let's write it this way. How do you establish number one? Well, it's easy. You take a derivative. Okay? So you just differentiate this function under the integral sign, and you see that f prime of x is equal to the integral from 0 to infinity rho of t dt over 1 plus xt squared, and then there's a factor of t and a minus sign. So that's f prime. Okay? So proving that f prime exists, well, I did more than proving it exists. I showed you what it was. Okay? However, what about property 4? How do you prove, this is something that you're not, this is a word that most people have not seen before, Herglotz. How do you prove that this function here is Herglotz? Well, it's actually fairly straightforward. Let's suppose x is equal to a plus ib. Okay? Then the function f of x is the integral from 0 to infinity dt rho of t over 1 plus xt would be a plus ib t, right? Which is 1 plus at plus ibt. Okay? Now, let's multiply the numerator and the denominator by the complex conjugate of that number. Okay? So let's multiply by 1 plus at minus ibt, 1 plus at minus ibt. Okay? And the denominator now, d of t, rho of t, the denominator is nice and simple. When you multiply a complex number by its complex conjugate, you get 1 plus at squared plus b squared, t squared. And in the numerator, you get 1 plus at minus ibt. You agree? You all see this? So that's really cool, because now I know how to take the imaginary part of f of x. The only thing in this integral here, everything here is real. The only thing that's imaginary is this little I over here. So if I take the imaginary part of f of x, what I get is minus, see that minus sign, minus an integral from 0 to infinity dt rho of t b, let's put the b outside, b t 1 plus a t squared plus b squared t squared. Okay, now everything in this integral is positive, right? T is positive because we're integrating from 0 to infinity. We're integrating over positive t. Rho is positive because, by definition, the weight function is positive. The denominator is the sum of squares, so that all that's positive. Everything here is positive. Okay? So this, all this junk over here is a positive number. Okay? So we proved that minus the imaginary part of f of x is proportional to b, where the proportionality constant is a positive number. Okay? So the imaginary part of f, let's put the minus sign in here. The imaginary part of minus f of x has the same sign as b. When b is positive, that guy is positive. When b is negative, this guy is negative. Okay? That's the proof that this function is a Herglotz function. Okay, it's very easy. So any questions about that? Yeah.
I don't see why this is useful.
Okay, that's not at all obvious. Okay, and it's a strange property, right? First of all, it's a funny name. Secondly, it's a strange property, and as I say, if you take a course in complex variables, the chance that you're going to come across this condition here is small, right? It's an unusual condition. Let me prove to you, let's see, to answer your question, let me show you something interesting. Okay? Let me first of all show you that the Herglotz property is a very powerful property. Okay? Let's I don't want to interrupt that discussion, but let me just claim here that that Herglotz property is a very constraining, powerful property. Okay? For example, there are lots of functions that are... Do you know what entire means? Does everybody know what the word entire means? Yeah. What does it mean?
The function is defined on the whole and there's a derivative.
There's a derivative everywhere, except at infinity. Okay? So the function is analytic everywhere. And there are lots and lots of functions that are entire. Okay? So entire means analytic for all finite complex x. Okay, for all finite complex x. So there are lots of entire functions. What's an example of an entire function? Well, polynomials. You know, these are functions that have no singularities, okay? So example is polynomials, e to the x, you know, sine of x, cosine of x, sinh of x, all these standard transcendental, elementary transcendental functions. Another example would be airy function of x, okay? Has no singularities, okay? And there are lots and lots of entire functions, okay? So, what if we have, this is to answer your question, what if we have a function that is, so if f of x is entire and Herglotz, then what if you have a function that's both entire and Herglotz? What happens now? Okay, it's an interesting question. Let's find out. Okay? So there are zillions of functions that have no singularities. But what if the function is Herglotz as well? Well, if the function is entire, that means it has a Taylor series. Okay, entire means f of x has a Taylor series of the form a sub n x to the n equals 0 to infinity. And this Taylor series converges for all x. Okay? Now, you know that we can write down x in polar form, right? You can say x is r e to the I theta. All right? So then this Taylor series is f of x is the sum from n equals 0 to infinity, a sub n r to the n e to the I n theta. Okay? Now, if the function, you notice in the definition of Herglotz, Herglotz says in the upper half plane, the imaginary part of the function is positive, and in the lower half plane, the imaginary part of the function is negative. And on the real axis, if the function exists, then of course it's neither positive nor negative, so it's real. So on the real axis, the function has to be real. So if it's Herglotz, a sub n is a real number, okay, because on the real axis, the function is real. Okay? So we can write the function in this form, and now suppose we take the imaginary part of f of x, because we want to know what sign the imaginary part of f of x has. So it is the sum from 0 to infinity, a sub n r to the n, sine of n theta, right? E to the I n theta, this thing is cosine of n theta plus I sine of n theta. So if we take the imaginary part, you get sine of n theta. Okay, so far? That's interesting. So we have been able to write the function, the imaginary part of f of x, as a Fourier series. Now, if it's Herglotz, okay, so Herglotz means that the sign of this, the sign, okay, so now you have to listen carefully to my words because there's two words sign here. the sign with the g of this sum from n equals 0 to infinity, a sub n r to the n sine of n theta is the same as the sine of theta. Right? That's because the sine of theta, okay, that's because the imaginary part of x, which is the imaginary part of r e to the I theta, is r sine of theta. Okay? So in the upper half plane, you know, the imaginary, if we're looking at the imaginary part of this, the upper half plane sine of theta is positive, lower half plane sine of theta is negative. Okay? So the sine of this is the same as the sine of theta. You agree?
Isn't it the sign of imaginary of minus f?
No. It's only true for a Stieltjes function that minus f is Herglotz. It's silly, but it's minus f that's Herglotz. That's because, remember, when we took the complex conjugate, we got a minus sign here. Okay? But in general, you say a function is Herglotz if in the upper half plane the imaginary part is positive. Okay. So the sign of this has to be the same as the sign of that. Okay? But here's a simple identity to remember. Simple identity is that n sine of theta is greater than or equal to sine of n theta. Okay, for these are both odd functions. For theta, theta greater than or equal to between 0, for theta between 0 and pi. Okay, and obviously if theta is less than 0, that is, lies between 0 and minus pi, these are both negative, but in absolute value, this guy is bigger than that. Okay, or to put it in a different way, n sine theta plus or minus sine of n theta has the same sign. Sorry about all the signs. Okay, this guy has the same sign as that guy. Okay, because since this is smaller than that, adding and subtracting this cannot change the sign. Okay? So if I wish, I could just tack on here plus, or I can put an n over here, because n is a positive number, and I could say n sine theta plus or minus sine of n theta. Okay? Now we're almost done. Let's take both sides of this and multiply, just multiply by, let's remember one identity first. Remember that, how many of you have seen Fourier series before? A little bit? A little bit? Okay. So d theta, you remember the basic identity for sines. So the integral from 0 to pi d theta sine of n theta times sine of m theta is, what do you get? That's right. You get 0 unless n is equal to m, right? In which case, okay, you get 0 if n is not equal to m, but you get pi over 2. And for our purposes, pi over 2, Schmeier, it doesn't matter, some positive number, when n is equal to m. Okay? So what we've argued is that this guy has the same sign as that guy, and I could also add plus or minus sine of n theta, and that wouldn't change the sign of the right-hand side. Okay? So here's the last step. Let's use the fact that this guy has the same sign as that guy, and let's multiply both sides by sine of n theta plus or minus n sine of, sine of theta times n plus or minus sine of n theta. Let's just multiply both sides of this by that, and let's integrate with respect to theta from 0 to pi over 2. Okay? Just do that. Okay. So from this orthogonality identity, on the left-hand side, what would we get? Well, the only thing we would get would be a1, right? Because sine of theta, when you multiply it and integrate, everything vanishes except for the case n equals 1, right? So you would get pi over 2 times a1 times r to the 1. Okay? That's all. Does everybody see that? Okay? And when you multiply by plus or minus sine of n theta, and you integrate, you get pi over 2 times a n times r to the n. Okay? Now, what we've multiplied by is positive, and we've integrated from 0 to pi, so that doesn't change the sign of anything, but you notice that on the left we have this. And we are claiming, but what would you get on the right-hand side? If you just have a sine of theta here, you would just have, n times pi over 2. That's all you'd have. Okay? And this has to have the same sign as that. Now, this guy is positive. That means this has to be positive. But this can't be true, right? Because if I go far enough away from the origin, I can take r so big that adding or subtracting this will change the sign of that. Does everybody see that? R can be made arbitrarily large. Therefore, contradiction. So the only resolution of this is that an must be equal to 0 for n greater than 1. And I think that gets a wow. Okay, that's amazing. So the only function that is both Herglotz and entire is utterly trivial. What we have shown is that f of x, so what's the conclusion of all this? All this implies that f of x is a plus bx, and that's all. Those are the only functions that are both Herglotz and entire, just linear functions. So Herglotz is a very powerful and constraining identity. It's really, really powerful. Okay? Not many functions. I mean, if you have an entire function, you better not tell me it's Herglotz. That's too much. Okay? There's nothing left. Okay, well, that's fine. But what are we going to do with that? Okay, so this is the game. Okay, so what I've shown you, so are there any other questions? So Herglotz, I haven't shown you why the Herglotz condition is relevant here, but I have shown you it's a really strong condition. It's very strong. Okay, so Where are we logically? If you have a Stieltjes function, it has these four properties. But now we come to an amazing theorem that takes, I don't know how many pages to prove. I don't think the proof is less than 50 pages. It's an enormous, very detailed proof. But the point is that if you have 1, 2, 3, and 4, okay, so if some function f of x satisfies 1, 2, 3, and 4, this implies that f is Stieltjes. Okay? The fact that a Stieltjes function has these four properties, that's not very difficult to prove. But proving the reverse, if you have a function that has these four properties, then f is Stieltjes, that's the hard part. That's like 50 pages of hard work. Okay? But I'm going to do I want to show you the first quarter of the first page of the proof. Okay? Because I want you to see where the answer comes from. Okay. The only thing is, how much you have seen, Sarah, you've reviewed complex variables? I did. Or you did, Tibra. Okay. So then you must have mentioned Cauchy's theorem. That's the source of all knowledge. Okay. All right. Cauchy's theorem is a fantastic theorem. And it is the first indication that complex variables is a beautiful subject, and it's a very powerful subject. And there's no analog for Cauchy's theorem in real variables. That's the amazing thing. So Cauchy's theorem says the following. It says, if you have a function, this is the complex x-plane, and you would like to calculate, or let's call this the complex t-plane. Complex t-plane. Okay. And you pick a point here, x. Okay? Cauchy's theorem says that f of x is equal to 1 over 2 pi I times the integral dt over times f of t divided by t minus x. This is an amazing fact. This is absolutely amazing. Okay? Why is it so amazing? This is an extraordinary fact. Okay? It says you do some integral along a contour that goes around the point at x. So this is some contour C. Any contour such that inside of the contour, this function f of x is analytic. Why is this so extraordinary? It says that you take all of the points on this contour. This integral is only on this line. Okay? These points that are going around the contour are not at the point x. And yet, the knowledge of the function at all of these points here is enough to tell you what f is at x. That's incredible. It's unbelievable. Okay, that's an amazingly powerful fact. Okay? In real variables, if you were talking about real variables, this would be utterly ridiculous. Okay? Because if you have a function f of x on the real line, and you say, you know, this is the x line, just real x, and here's some point x, this is saying that if you knew f on one side of the point, you know, let's call this point b, so you knew f of b, and here you knew f of a, and you make some combination of, you know, here's the point a, and you know f at the point a, and here's the point b, and you know f at the point b, could you use the knowledge of f at a and f at b to determine f at the point x? That's absurd. That's completely absurd. okay? But in complex variables, it's true. That's amazing. Yeah.
So in complex variables, we have the Cauchy-Riemann equation, and we can use that as a boundary condition, and basically extrapolate the values inside. So
That's
if in
right.
the real case f was a solution to some first order equation, then we could
relate, we could integrate from x to b and from x to a and relate this number and this number to that number, to the value of the function there. But in real variables, we don't have any such thing. So we could still have a function which is infinitely differentiable, but we don't have the equivalent of the Cauchy-Riemann equations. Okay? So indeed, this is the consequence of solving, if you like, the Cauchy-Riemann equations, which are fancy, very fancy equations. Okay? By the way, however, this property of when you know everything on the outside, you know the value of the function on the inside, can you give me a real equivalent of that? Can anybody in the class here give me a real equivalent? That is to say, imagine you knew nothing about the number I. Okay, you're a real analyst, not a fake one. Okay, and so what would be an example?
Stokes theorem.
Well, but which, I mean, in physics, where, that's a mathematical statement, but in physics, where do we have, and if you know everything about the outside, you know everything about the inside.
Electromagnetism.
Very good, but which electromagnetism? I mean, there's a specific case in not in general.
Gauss law.
In
Electrostatics.
In electrostatics, that's right. Time-independent electromagnetism, that's exactly right. If you know the voltage everywhere here on some curve, okay, or on some surface, it could be in three-dimensional space, two-dimensional space, we don't care, then you know the voltage everywhere inside. So in time-independent electromagnetism, electrostatics, not time-dependent, but time-independent, then you know everything about the inside. And people also call this holography. Okay, in fancy string theory language, this is holography. But basically, if you know what's going on the outside, you know everything about the inside. So the boundary values here determine what's going on inside the problem. And this is a feature of the equation del squared phi equals 0. Okay, if you're solving Laplace's equation and you know the value of phi everywhere on the boundary, then you know the value of phi everywhere in the interior. And that is the real analog. And as Tibor said correctly, you need to have a differential equation that relates the boundary to the interior. And in pure real variables, this is the equation. And indeed, if you iterate the Cauchy-Riemann equations, what do you get? Laplace's equation. So this is very important. All right. So here we have this wonderful, wonderful identity. And it says that if you know f of x everywhere on the boundary, then you know f of x in the interior. So are you all with me? Follow that? Now, in our case, so here I'm using the fact that the function is analytic in the cut plane. But I forgot to write down the cut. This is the one place, this cut is the one place where f is not analytic. Okay, but everywhere else, f is analytic. Does everybody see that? Okay, good. Now what? Well, you know in complex variables that you can deform the contour. So I could push this contour out to this contour. And I could keep pushing it out. But this contour cannot pass through this cut on the negative axis. It can't do that. So if I continue to push the contour outward, the contour will wrap around this cut, but it can't pass through the cut. can't cross into a region where the function is not analytic. So this is what I will do. I'll make the contour very big so that it looks like this. So here's the cut. Here's the point X. And the contour is a gigantic toilet seat. Okay? So it looks like this. Okay? And we should get the direction of the contour, right? That's the direction. Okay, did you follow that? Okay, now, the outside part of the contour is some huge circle of radius r, and the inside of the contour is some little circle of radius little r. And you know what I'm going to do. What am I going to do? I'm going to make capital R very big. Okay, I can make it very, look, it's even bigger. No, I'm just kidding. Forget that. Okay. I'm going to make R very, very big. And I'm going to make little r very, very small. And what I claim is that the contribution from this part of the contour is going to go to 0. I claim that there's no contribution to the integral as r goes to infinity. The contribution along this part of the contour goes to 0. Can you tell me why that's true? Why would that be true? Why don't I get any contribution to the integral as this contour gets very, very big? Yeah?
The function goes to 0 faster than r goes to infinity.
That's right. It's because of the integrand. Okay? Because we know that this function goes to 0 at infinity, that is property 2. Property number 2, this function is going to 0. Right? And the denominator is going to 0 like 1 over r. But the length of the contour is blowing up like r. Right? So we can bound the integral. Okay? The integral is bounded by the length of the contour times the maximum value, maximum value of the integrand on the contour. The maximum value of the integrand is 1 over r. That's because we have a 1 over t minus x, and x is as big as r. Or t is as big as r. Okay? So t is growing like r. Okay? Times f. Okay? And that is something else. F is going to 0 as r goes to infinity. Okay? And that's by property number 2. So this goes like 1 over r, and this is also going to 0. And how long is the contour? How long? Well, what's the distance around a circle? It's 2 pi r. Okay, so the r cancels the r, and f is going to 0 at infinity. Bang, by property 2. So by property this is property number 2. Property number 2 here. There's no contribution here. And the contribution along here goes to 0 because the length of the contour is going to 0. Wait a minute. Hang on a second. The length of the contour is going to 0, but what if the function is blowing up at 0? The length of the contour is going to 0, but what if the function is blowing up at 0? Then there might be a contribution just from this little contour that just goes around this little half circle. How do we know whether or not the function is blowing up at 0? Well, we know it's not blowing up at 0 because at 0, it is asymptotic to the series. And therefore, the first term in the series, which is a0, this says the function is asymptotic to a constant as x goes to 0. So it's nothing bad is happening at 0. Okay? That's property number 3. Okay? So the integral along this part of the contour is going to 0. And all we're left with is an integral that goes from minus infinity up to 0, and then from 0 back to minus infinity. Got that? Does everybody see that? So we have just shown that f of x is 1 over 2 pi I times an integral from minus infinity up to 0 dt. You notice this is a real integral going from minus infinity up to 0 over, as you see, t minus x, and f of t. Here we're integrating f along t plus a little bit that's going to 0. It's just a teeny bit above the imaginary axis, minus f of t minus a little bit. You see that? But the function is Herglotz. So this, in the upper half plane, is a positive thing. This is a negative thing. And as you go to 0, you are calculating the discontinuity across the cut, okay, which is pure imaginary. Okay, just pure imaginary. And so this is this is called the discontinuity, I times d of t, the discontinuity across the cut. This thing minus that thing. Now that's interesting because this I here cancels that I over there. And so we're left with the statement that f of x is equal to 1 over 2 pi integral from minus infinity to 0 dt over t minus x times the discontinuity in t. Okay, now I'm going to do one last thing, then I'm going to stop calculating because I'm tired. Okay, but one last thing. Let's make a simple change of variables. Let's replace t by 1 over s, or let's say minus 1 over s. Okay, I can do that. Okay? So this becomes 1 over 2 pi. Now, when t is equal to minus infinity, s is equal to 0. And when t is equal to 0, s is equal to minus infinity. Got that? And t becomes, dt becomes 1 over s squared ds, and the denominator becomes 1 over s minus x. Minus 1 over s. S is minus 1 over t. Oh, sorry. This is infinity. Yeah. Okay. Yeah, sorry. You're right. Okay. So now we have dt becomes 1 over s squared ds. T becomes minus 1 over s minus x, right? And this is d of 1 over s with a minus sign. Okay? Now let's multiply, let's simplify the denominator. Okay? So this becomes 1 over 2 pi integral 0 to infinity ds. This s squared is in the denominator. Okay? So I get 1 plus xs d of minus 1 over s divided by s with a minus sign. There we go. Okay. So let's take this 2 pi out, by the way, and let's put the 2 pi over here. Now you know what I'm going to do. I'm going to give that a name. And just for laughs, I'm going to call this rho. I can call it rho. If I wish, I can call it anything I like. In particular, I can call it rho of s. So I've proved to you that f of x is equal to the integral from 0 to infinity ds over 1 plus xs times rho of s. Ha! There we go. It's a Stieltjes function. Right? Good point. Now we've gotten to the hard part of the proof. You see, unfortunately, we're not done, as you point out. We're not done yet. There's more to do. Okay, what we have to do is prove that this function rho is positive for all t greater than 0. And we have to prove that all the moments of rho exist, which we haven't proved yet. We have to prove that. Okay, that's hard work. I'm not going to show you. Okay, this is something you should do in the privacy of your own bedroom. It's not something to be done on a blackboard. Okay, so when I say there's more to do, what I mean is there's lots more to do. Okay, you have to show that rho is positive. That is, you have to show that rho is positive, and that that the integral of t to the n rho of t dt, which is a sub n, you have to prove that this guy exists. And that's a lot of work. And this is where the Herglotz property comes in. Okay, now you ask me where we need something powerful. Right? We need a new and very powerful fact, and we haven't got it yet. Okay, all we did was use Cauchy's theorem, and Cauchy's theorem is completely general. We need a powerful new fact. Okay, and Herglotz is it. Okay, so now the question is, all right, what we have just shown is that if f of x, we haven't shown it, but I've stated it. If you have a function that satisfies 1, 2, 3, 4, it's a function of Stieltjes. Why do we care? All right, so it's a function of Stieltjes. Why is that so great? Okay, this is the reason why it's so cool. Okay, so let's put. Okay. Okay, the reason why, yeah. Because I've used the Herglotz property. Remember, the function, if I have a Herglotz function, it's going to be real on the real axis. Okay, if it exists. Okay, so the Herglotz tells me that there's a symmetry between the upper half plane and the lower half plane. It's positive imaginary here, negative imaginary here. And as I approach the real axis, the imaginary part, if the function exists, the imaginary part is going to disappear. If the function doesn't exist, then there's going to be a balance as I approach the real axis between the positive and imaginary, the function in the upper half plane, the function in the lower half plane. And if I subtract them, the real part cancels out. And all that's left is the imaginary part of the function. Okay, so if the function doesn't exist, what can happen is that on the real axis, remember the function doesn't exist here. So as I approach the real axis here, the real part of the function vanishes. I'm sorry. The real part of the function going this way is the same as the real part of the function going this way. And all that's left is the imaginary part. Okay? And here we have a positive imaginary part, and here we have a negative imaginary part. And that's the point. Okay? And so when I subtract the function just above the real axis and the function just below the real axis, the real parts cancel out, and the imaginary parts subtract, and the difference, this difference is pure imaginary. Okay, so that's where this factor of I comes from. There's no real part, just an imaginary part. No, we don't know. We don't know whether, well, we could actually. We haven't tried to. Okay, we have not tried to say anything about the sign of the imaginary part. In fact, the imaginary part here is positive, and so we can try to come up with some information about the sign of t. Okay, but I'm not going to pursue that anymore. But we can talk about it afterward if you like. Okay. So, but the question is, who cares? I've just been proving theorems for you, but who cares about these theorems? Why do we care about this? And the reason is this. Mr. Stieltjes showed that if you take a function of Stieltjes, this is a Stieltjes function, and you expand it into an asymptotic series, a sub n x to the n, 0 to infinity. If you take f of x, you expand it into a Stieltjes series, okay? And now you pod A. Okay? So you construct the pod A table. That is, you construct the Pnn of x, and you also construct Pnn plus 1 of x. Mr. Stieltjes showed that this converges in the cut plane. So for any x is anywhere in the cut plane, like here or here, anywhere, this sequence converges in the cut plane as n goes to infinity. It converges. Okay, that is a fantastic result. Okay, and furthermore, obviously, this also converges in the cut plane as n goes to infinity. And he showed more. In addition, okay, also, for real x, if x happens to be a real number, he proved, if this is n, that Pnn of x, this is only true for real x, of course, the pod A's will be real, and they will converge monotone downward. So this sequence, Pnn of x, converges monotone downward. It's a monotone decreasing sequence. And Pnn plus 1 converges as a monotone increasing sequence. And it converges. Okay? And furthermore, he showed that all of the Pn plus 1, all of the Pnn plus 1s are less than all of the PMMs for all n and m. So all the terms in this sequence are less than all the terms in that sequence. You know, the sequences don't cross each other. You see what I'm saying? So this guy is converging upward, that guy is converging downward. This is fantastically powerful, and there's a tremendous amount of mathematics to prove this result, but that is true of Stieltjes functions. So if you take a Stieltjes function and you expand it into a Stieltjes series, and you pod A the series, these things converge. Okay? But this is the really interesting part. Here's the but. The but is that we don't know whether or not this thing which is converging to a limit and this thing that's converging to a limit, we don't yet know that it converges to f of x. It just converges. This would be very, very, very disappointing if it didn't converge to f of x. But we want to know whether it converges to f of x. All I said was it's a sequence with a limit. Yeah? No, in the cut plane. Okay, sorry. Let me emphasize that. I drew the cut over here. It converges, okay, in the cut plane. Nothing, we don't know anything about negative x. Negative x. Oh no, this is just a special case of this. Okay, so again, this is only for positive x, for real positive x. We cannot use the PADE for negative x. And that's because the function itself is not unique for negative x. There's a cut. So it's like the square root function. It has a cut. Actually, it has a logarithmic type of cut. So it has many different values on the negative axis. We can't determine which value is the right value or anything like that. Okay? So we have to stay away from the negative axis. But in the cut plane, f of x converges for all complex x in the cut plane. It converges on the real axis, and it converges in a monotone fashion, the real positive axis. Yeah? No. No, that's the problem. So what we don't know, you notice how I drew this? This is converging, you know that a monotone sequence, which is bounded, must converge. It has to converge. And it's bounded below by this inequality. So this has to converge to some limit. We call that limit number 1. This has to converge to some limit, limit number 2. How do we know whether or not limit 1 is the same as limit 2? And how do we know whether or not it's the right answer? And it turns out we don't know yet. So we're still not quite there. Okay? So we need quintessence. Okay, now if you go to a talk on quantum field theory, you'll hear words like quintessence, the fifth force, the fifth property. Remember, I mean, this goes all the way back to Aristotle. Aristotle had 4 of everything. Isn't that right? You know, the 4 elements. What are the 4 elements according to Aristotle? Fire, water, air. And the human body contains 4 fluids: bile and phlegm and blood and whatever, right? 4 and there are 4 dispositions, 4 moods. You know, what are they? I don't know. Happiness, sourness, and they correspond with the 4 fluids and the 4 elements. There's 4 of everything, okay? Which is great. But 4 is not enough. We need, you see it? 5. Quintessence. So we need one more thing. Sorry about that, but this will finish the lecture. What's the 5th thing? Well, an easy way to say it is, if the moment problem has a unique, so this is a technical term, the moment problem has a unique solution, then the upper limit equals the lower limit equals the correct answer, equals f. And in the complex plane, the PADEs converge to f of x, and everything works. So this is and now this is where things get a little technical. This is a sufficiency condition. So if the moment problem has a unique solution, then the PADEs converge to the function that the asymptotic series represents. So you ask, what's the moment problem? Okay, so this is the moment problem, and it's a very, very famous problem, and really very little is known about it. That's the amazing thing. This is the moment problem. The moment problem is you take this system of equations. A sub n is the integral from 0 to infinity, rho of t dt times t to the n. You give me this for n, so this is given for n equals 0, 1, 2, blah, 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 all the way up to infinity. Okay? So you give me these numbers. And the problem is to find a rho of t, find that function, I don't mean a, find rho of t. That's the problem, such that rho of t is positive. Okay? That's the moment problem. This is a really hard problem. Okay? I give you these numbers. Okay, now remember the intelligence test I gave you? Remember that? So I use that as a sort of a subtle introduction to this, and that's just a taste of the fun that you can have. But this is a classic problem, and nobody knows the complete solution to this problem. This is a really, really hard problem. Okay? So only if the moment, so if we can show, not only if, but if we can show that the moment problem here has a unique solution rho, then everything works. Then the PADEs converge, and they converge to the right answer. Okay? So let me show you an example where the moment problem does not have unique solution. So I made some lecture notes. Okay? Okay, so this is... I don't usually like to lecture with notes, but I had to make lecture notes. Okay. So let me give you an example of a moment problem. Okay? The moment problem is a sub n is 8n plus 7 factorial. Okay? This is some random moment problem. So this is a bunch of numbers for n equals 0, 1, 2. And the problem is to find rho of t. That's the problem. I gave you the moments. You have to solve the problem. Got it? That's the moment problem. All right, so let me write down the answer. Rho of t equals e to the minus t to the 1/8 power over 8. That's the solution. And you can pretty much do this in your head. If you plug it in, do the integral, make a change of variables, replace t to the 1/8 by s, do the integral, you get the factorials, blah, blah, blah. Everything works. Okay? But here's the unfortunate part of the answer. This isn't the only answer. Okay? In fact, there are an infinite number of answers to this problem. And they are a times e to the minus t to the 1/4 times sine of t to the 1/4. And a is any number between, now you see why I had to make up lecture notes, between minus 0.14761 and 1.21584. Okay. So what's happening here? You see, what's happening is, if you do an integral of this, what do you think you get? 0. You get 0. How could you possibly get 0? It's because this function is not a positive function. However, if you add this function to that function, the overall thing will be positive if A lies between these numbers. Now, I don't even know if this is the most general solution to the moment problem. All I've shown you is that the moment problem doesn't have a unique solution. Okay? So long as this is true, so long as this inequality is true, this guy is strictly greater than or equal to 0. And by the way, I should put dots over here. I mean, this is not, you have to work it out on your pocket calculator. Okay? So this is very disturbing. How do we know whether or not the moment problem has a unique solution? That's what it's come down to. Okay? Nobody knows the complete answer to this question. However, there is a partial answer which is very satisfying. Here's the partial answer, and the partial answer is called, I love this, by the way. This is called, no, it's not quite. Okay, Mr. Karleman found a partial answer to the problem, and it's very simple. If A sub n, so the statement is, if A sub n grow no faster than 2n factorial, then the solution is unique. A solution, you understand, to the moment problem. Then that solution is unique. Got it? That's the complete theory. I've given it to you. There's hardly anything more to be said. Of course, maybe you can find a better condition than the Karleman condition, but I want to show you why it's relevant. Okay, why is this relevant? All this is mathematics. I want to show you what the physics is, and that turns out is very, very easy. Okay, so here's the physics. Do you remember that this is a course on physics? Okay. Imagine you're solving the Schrödinger equation. Okay? There's the Schrödinger equation. And you're trying to find the eigenvalues E. Those are the energies. The most important thing in all of physics is the energy. And you're trying to find the energies. So you want to know, what is E? But you can't solve that differential equation. So what do? Now we go right back to the beginning of this course. You can't solve it, so you decide you're going to put in an epsilon. And now E becomes a function of epsilon. And you assume that you can solve the problem with epsilon equals 0. So a typical problem here would be, minus psi prime prime plus x squared over 4 psi plus epsilon psi equals E psi. Okay, and that's a problem you've played with. This is an example. Okay, and you are doing perturbation theory, and you are calculating, you work very hard, and you find that E of epsilon is given by the asymptotic series A sub n epsilon to the n. If we pade, sorry, do I have a? Oh, sorry. I forgot to put in the hard part. Sorry. It was there, actually, but I had written it in invisible chalk. So, okay. So the question is, we've done perturbation theory. You've calculated these coefficients. You find that this series is a divergent series, but it is asymptotic as epsilon goes to 0. Okay. And you can pade this, and you could even get an answer. How do you know it's the right answer? Okay? So, once again, I can refer you to various papers that have been written, but the point here, let's raise this up. The point here, you can show rigorously that you can show, and I can refer you to papers in which it's been proved rigorously. It took it took 10 years basically, but you can show that E of epsilon is analytic in the cut plane, etc., that this series is asymptotic in the cut plane as epsilon goes to 0, etc., etc., etc. You can prove all that you need to prove, and you can even show, and this is what I want to show you, this is how I want to end the class, you can even show that this function E is a Herglotz function. Okay? And it turns out that's the easiest thing to show. So I want to prove that much to you. I want to show you why is it that E is a Herglotz function, which is the important thing that we need to prove. Why is that true? And we can prove it by just taking this Schrödinger equation. In fact, let's make it easy. Let's lower this guy. Okay, let's take this equation. Now remember, epsilon is a complex number. But let's so therefore psi is complex. But let's take this equation and just multiply by psi star. Okay? And let's integrate from minus infinity to infinity. Okay? Straightforward. So what do you get? You multiply this equation by psi star. The equation now reads psi star, with a minus sign here, minus psi star of x times psi prime prime of x plus v of x psi star psi plus epsilon w of x psi star psi equals E psi star psi. And then we integrate. Integrate, 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 integrate. Got it? Now, let's integrate this by parts. So we'll take one derivative over here, and we get plus, this guy becomes plus psi star prime times psi prime, plus all this stuff. I need to write that. Okay, now what am I going to do? Let's look at this very carefully. This is psi star prime times psi prime. Star is a real positive number, right? Remember, A star A is real and positive. Therefore, this is a positive number. This guy is a positive number, and for V positive, we can actually extend this to V that is not positive. But for our example, for this simple example here, not so simple, this is also positive. So this guy is a real positive number. Same with W. W is positive. Psi star psi is positive. So this is a positive number. Okay? And this is a positive number. So now, let's take the imaginary part of this entire equation here. What do we get? We get some sort of positive number here times the imaginary part of epsilon is some other positive number times the imaginary part of E. Aha! We just showed that the sign of the imaginary part of the energy is the same as the sign of the imaginary part of epsilon. Same sign. They're proportional to one another. That's the proof of Herglotz. In fact, deep in quantum mechanics is the Herglotz property. And this is one of the ways in which I'm unhappy with the way complex variables is taught. Because a truly important theorem for physicists is a theorem about the eigenvalues of the Schrödinger equation. The energies, this is a very general property, the energies are Herglotz functions. That's why we can do Pade, and that's why we can extract the answer in physics problems. Of course, if you're a mathematician with a diseased mind, you can think of examples where the Pades are not going to work. Okay? Okay. However, there's one last thing. There's one last thing, and that's where I'm going to finish. Just because we know that all four of these properties, let's push this up. So in physics, you can prove all four of the properties. Therefore, the Pades converge. But how do we know they converge to the right answer? You need quintessence. You need to go beyond Aristotle. Okay? Why is the fifth property true? Okay? What do we need to know? We need to know how rapidly do the coefficients in this perturbation series diverge. And for this problem, for this example problem, the anharmonic oscillator problem, this one here, I showed you, I stated in class, I haven't proved to you, but I stated in class that a sub n grow roughly like n factorial times 3 to the n times minus 1 to the n, so on. And this is the key thing. N factorial grows less rapidly than 2n factorial. That's why everything works. So there are some problems where the perturbation series might grow too fast. Okay? So what's an example? So for epsilon x to the, for the epsilon x to the 4 theory, a sub n grow roughly like n factorial times a constant to the n. For epsilon x to the 6th, a sub n grows like 2n factorial epsilon, times a constant to the n. Some constant to the n. Okay? For epsilon x to the 8th, however, a sub n grows like 3n factorial times some constant to the n. So there's an example of a problem where the Pades converge, but they don't converge to the right answer. Now, in fact, what you can prove, this is the last thing I'm going to tell you, what you can prove is that if you make a plot of n, it is always true that Pnn is going down, Pnn plus 1 is going up monotonically. So if this is n, the Pades are, the n Pades are going down, the n plus 1 Pades are going up, and these are approaching one limit, these are approaching another limit, and you can prove that the exact answer is strictly less than L1 and greater than L2. What you can prove is that the exact answer lies somewhere in there. It's not outside. That you can prove. But you don't necessarily know where the exact answer is. So, does anybody, so I'm just going to conclude, I'm going to show you this next time, but I'm going to conclude with an interesting puzzle here. Do you know why perturbation theory for this problem here, this anharmonic oscillator problem, this guy, do you know why the perturbation coefficients are growing like n factorial times a constant to the n? Do you know why, if we had an x to the 6th theory, it would be 2n factorial? Do you know where's the factorial, basically, where's the factorial coming from? Yeah.
Roughly when we calculate perturbation theory coefficients, we are calculating the integral of the wave function times some power of the potential.
That's true.
So the wave function is approximately exponential, or?
Well, the wave function is actually not a Gaussian, though. The wave function is for an x to the, we know from WKB theory that for an x to the 4 potential, we know that for large x, WKB says, remember we did this in class, we know WKB would, asymptotically, it would go like 1 over the 4th root of x to the 4th times the exponential of the integral of the square root of x to the 4th. So this goes like 1 over x times e to the minus x cubed over 3. That's how so it's not a Gaussian. So it's hard to make an estimate like what you're talking about. But here's the guts. The argument actually is easiest to understand in quantum field theory. And that's an argument I'm going to give you next time. Turns out that what we're really doing when we're doing perturbation theory is adding up Feynman diagrams. And when we're looking at the coefficient of, when we're looking at A sub n, we're adding up all the graphs having n vertices. Why does A sub n diverge like n factorial? Because, roughly speaking, there are n factorial graphs. That's all. You're adding up all the Feynman diagrams, and there are n factorial of them. For an x to the 6th theory, there are 2n factorial graphs. For an x to the 8th theory, or you have learned phi to the 4 theories, and phi to the 6 theories, and phi to the 8. For phi to the 8 theory, there are 3n factorial graphs. And this is a 2-minute calculation. We can calculate, roughly speaking, the number of graphs. That's the problem. There are too many graphs. So you have a lot of work to do. Okay? Yeah.
You said that for the anharmonic oscillator, when we had x to the 8, you said that it converges to some answer, but it's not the right answer.
That's right. So this limit converges, the PNNs converge to this limit, L1. This converges to L2. If you actually calculated these two things, these two limits differ by, I don't remember exactly, but maybe 10 or 20%, something like that. They're pretty far off. And the correct answer really lies roughly in the middle, but not exactly in the middle. It's somewhere around here in the middle.
But how can we be sure that the correct answer is between them?
Oh, that is a rigorous result. Okay, that I'm not going to prove. That is much too hard for me to prove to you. And it would be, it would be a real struggle for me to try to prove it to you. You have to go back to the really rigorous work that Stiltjes did. But all of this stuff, when I say Mr. Stiltjes showed, I think he showed this mostly in his thesis. Guy was really smart. Really smart guy. Okay? All this stuff, and among the things that he proved rigorously is that if you have a function of Stieltjes, that these PADEs converge and that the correct answer is trapped in between. That's what he showed. Okay? But unfortunately, if L1 is not equal to L2, which is the case when there is not a unique solution to the moment problem, that is, in the case when the Karleman condition is not satisfied, we don't know a simple way to get the right answer. And we have to use even more powerful methods than PADE. And we have to go to information theory and, you know, I mean, this is really interesting. How do you get the information out? How do you suck the information out of these